So good morning. Welcome to the fifth series of EFCE Spotlight Talks. Today's topic is on static electricity in industry. And it's going to be chaired by Pedro Llovera-Segovia. He's the chair of the Working Party on Static Electricity in Industry. So firstly, who am I? I'm the current Scientific Vice President of EFCE. My background is in process safety. I've had experience of more than 30 years in industry and 5 years in academia. And I've been involved with EFCE for more than 20 years and a member of the executive board for 10 years. So the scientific vice president is the focal point of EFCE. So just to give you some background to the Spotlight Talks, many of you may not be familiar, and maybe the first time that you've dialed into this. So EFCE itself, firstly. So what is EFCE? EFCE is the European Federation of Chemical Engineers, and it doesn't have individual people as members. The memberships of EFCE are actually the national associations representing the chemical engineering profession across Europe. So, for example, in the UK, it would be IChemE. For France, it would be SFGP, Germany, Techn, and so on. So it's the national associations of the members rather than individual people. So EFCE represents more than 30 countries across Europe, and in total, it represents more than 100,000 chemical engineers in the profession. So, in terms of EFCE activities, the engine room is really the working parties and sections. This is where most of the activities is actually taking place. So working parties, which is being the working party is organizing this particular webinar today. So working parties are groups within EFCE which focus on specific topics within chemical engineering. So for example, there's a working party on thermodynamics, the working party on loss prevention, and so on. And their job is to share and promote knowledge, expertise, and best practice within their particular topic area. So as well as working party, there are also something called sections. Sections actually cover very much wider issues rather than single topics, where they are they require a more multidisciplinary approach. So, for example, there's a section on energy, there's another section on food, and we have a number of new sections just starting up in the organization this year. In total, there are 20 working parties and 7 sections, and covering these activities, there are around about 1,000 volunteers who are all experts in their fields, drawn from industry and academia across Europe. So just to give you some background to the different activities that EFCE are engaged within in terms of conferences, seminars, and workshops. So the biggest event, I guess, that we organize every 2 years is we have a major conference, which is the European Congress on Chemical Engineering. And we hold this in conjunction with the European Congress on Applied Biotechnology, so ECAB. So it happens every 2 years. This year, we have one this year, and it's being held in Berlin in 17th to 21st of September. At the moment, we have 9 topic areas running in this conference, and there will be 15 parallel sessions. So this is a very, very big conference covering all topics of chemical engineering. We also organize a series of one-day events known as the European Forum on New Technologies. So this is, as the name implies, it looks at hot topics, new technologies in chemical engineering. There have been 5 so far, but the next one is coming up. The 6th one is to be held in Palermo in October, and that's going to be on energy, environment, and digital transformation. And then finally, what we're on now is just a background to the Spotlight Talks. So Spotlight Talks were devised by and overseen by Martine Pook. She's on the running the webinar today. So thank you, Martine, for this. And it was really initially established to maintain communication throughout COVID, when we couldn't have face-to-face meetings, organizing activities through webinars. But they proved so successful, we decided to keep running them as a regular series, and they've been very successful. There are a series of half-day webinars holding over a number of consecutive days. So this is week 2 in this particular series. And as we said, they're delivered by working parties and sections. The current series is the 5th series. We have 8 webinars in this series, running from, as I said, from 24th of May to 5th of June. In terms of up to this series, we had more than 600 attendees across the different first 4 series. And if you want to go back and check out any of the other webinars in the past, you can all find them. They can all be found on the EFCE YouTube channel. So that's really all I want to say. I'd like to hand the session over now to Pedro, and have a great session. Thank you.
Thank you, Mike. I'm going to share my screen. Okay. So, is it okay? You see my screen? Yeah. So, so thank you, Mike, for this introduction. It's my pleasure to introduce this Spotlight talk, which for us is the 3rd one in this series of Spotlight talks. It's the 3rd devoted to electrostatics in industry. I would like to thank EFCE for the opportunity of organizing this webinar, and especially Mike for his presence, and also Martine for her great effort. I would also like to thank the Energy Technological Institute, with which I work on electrostatics for many years, and of course, thank all the attendants to this webinar. One of our aims of these webinars, at least for us, is to build a scientific and technical, let's say, electrostatic community. So I strongly encourage you to participate with questions during the webinar. We will be very happy to answer any question, not only very specific or specialized questions, but also if you have basic questions, fundamental questions for people who are starting in this field, and they are very welcome for this. Don't be afraid. You can ask questions. You have the section in the Zoom session. You have the question and answers or the chat to ask your questions. We will collect them. You cannot speak, so you only can write if you have questions. We will collect them during the presentation of each presenter, and at the end of each presentation, we will have some minutes for questions if there are. Today we have these 3 presentations. 4 Holdstocks will focus on flexible intermediate bulk containers, safety measures. So it's about risk. There are still incidents with FIBC, although we know the rules and the solutions. So I think it will be very, very interesting. Then I will present myself. I will present a talk about electrostatic comfort. Sometimes it's seen as a minor question, but it's a very universal question. Everybody has felt electrostatic discharge. And up to now, but this is changing, there were no standards addressing this specific problem of comfort, which seems sometimes minor, but it can become a real problem in some situations. And the last presentation, which will be made by Gustavo Ortega-Bran, it's about materials. So we always have these 2 points of view on electrostatics, from one side problems and from one other side applications. In that case, it's a very interesting material, very smart material. With it is piezoelectric, but made with electrostatic charge. So he will show us how it works and what are the properties and applications. Before continuing, I would like to say some words about the spotlight talks, but already Mike told you. You have here the list of all the webinars. We are in this one in static electricity industry. There's 3 more going on the next days, but you can see all of them, watch them again at the YouTube channel of the EFCE. Our working party is devoted to the problems and applications. Always the 2 questions: problem and application of static electricity in industry. So it covers safety incidents, explosions, damage to electronics, also understanding how electrostatic process work in industry, what are the new standards and applications. Then you have specific fields where electrostatic is important, like precipitators and separators, ozone generation, electrospinning, electrospraying. More advanced or very, let's say, specific fields like electrohydrodynamic flow control by electrostatic discharge or electrostatic fields. Also, in electrical engineering, high voltage direct current is also including some concepts and problems very well known in the electrostatics fields, but also in aerospace industry. Sometimes we see works on Mars, on Moon exploration, and problems with electrostatics and electrostatic cleaning of solar panels, for example, biological application, and so on. So many fields. It's a very, let's say, horizontal field. So sometimes presentation seems very different, but they all share the same fundamental knowledge about electrostatics, electrostatic charge. As Mike told you before, the EFCE organized this year the largest conference, the European Congress of Chemical Engineering, shared with the European Congress of Applied Biotechnology. You can see the information on the screen. Today is the last day for abstracts. I think for poster presentation today, so you can still present something for the conference. Another conference which is important for us is the Electrostatic Conference. So our working party organizes every 4 years an international conference on electrostatics in industry. And we are in close coordination with another international conference of electrostatics organized by IOP, the Institute of Physics in England, in United Kingdom. We work together very close. We promote the field each other. So next one is also this year in November. Paul is also the contact person. He will probably say some words in his presentation today. I will just introduce our first speaker, Dr. Paul Holdstock. He will give the talk about FIBC standards and rules for safe handling of materials. He graduated at the Manchester Polytechnic in 1987. Then he joined the Shirley Institute, which is now a part of the British Textile Technology Group, as a research officer in the electrostatic laboratory, so many years working on electrostatics. He completed his PhD on electronic damage caused by electrostatic discharge from textiles in 1999. And now he operates his own business, Holdstock Technical Service, and he's an active member of BSI, CNN, CNELEC, ISO, and IEC technical committees. He works very hard on electrostatics. So, Paul, I will give you the hand for the presentation. I'll stop sharing my screen and the floor is yours.
Thank you, Pedro, for that introduction. And also thank you to EFCE and the Working Party on Static Electricity in Industry for inviting me to give this presentation today. The motivation for my talk today was an explosion that occurred at a paint factory, and this involved flexible intermediate bulk containers, or FIBC, and it occurred to me that I've worked for many years in standards and was the convener of the working group that developed an international standard on FIBCs and safe handling guidelines for FIBCs. And it occurred to me that maybe with incidents like this still occurring, perhaps there was a need to raise awareness of the standard, and perhaps for those that are familiar with the standard, just remind them of exactly what the guidelines are. So that was really the motivation for this talk. So I will explain a little bit about this explosion, but then concentrate on the main standard, which is an IEC standard 61340-4-4. I'll also mention some other national and international standards. I'm not going to go into too many details about those specific standards, because essentially they contain the same guidelines and the same important information that's contained in the IEC 6134044. And then in terms of the actual detail, I'll look at the requirements for earthing or grounding, both of the FIBC themselves, but also earthing personnel and other conductors. And just a note, I've said on the slide there, earthing and grounding. From our perspective and how we deal with electrostatic hazards, earthing and grounding mean the same thing. There are synonyms. I know in some applications, ground and earth mean slightly different things, but for our purposes, earthing and grounding mean the same thing. I'll try to stick to one term to avoid confusion. I'll use a term earthing because that's what we use in the standard. But please forgive me if I do slip and mention ground or grounding at some point. I do actually, that it's all the same. So please don't be confused about that. So let me just clear up my screen a little bit, because I've got too many things open here. And I can't see my own slides. There we go. So this explosion, it occurred just over 3 years ago at a paint factory in the UK. And the explosion severely injured one person who spent many days in hospital with quite severe injuries, life-threatening at the time, and certainly life-changing injuries, and spent many days in hospital and many months away from work. An investigation conducted by the Health and Safety Executive, that's the regulatory body in the United Kingdom, found that the explosion was caused by an electrostatic spark being generated when the employee was emptying resin pellets from an FIBC into a mixing vessel. The HSE said that the company had failed to put sufficient measures in place to control the risk, and that included a failure to control the flammable vapors through a correct extraction system, but also failure to use effective electrical earthing of the bulk bag. And this led to the buildup of electrostatic charge, which in turn led to the spark discharge. And it's that aspect, this failure to earth the bag, that really got my attention, because that is one of the fundamental controls that we have in electrostatics, or to control electrostatic risks, is this aspect of earthing. So that is what led me to believe that there perhaps was some requirement to raise the awareness of the standard and what the standards actually say. So just to finish up with this explosion, thankfully the employee is now returned to work and is being supported through the company's on-site occupational health provision. The company itself pleaded guilty to breach of health and safety regulations and was fined £800,000 with £14,000 costs. So this accident was costly, both in terms of the human impact, but also in terms of the financial impact on the company. And it was the first time in the 120-year history of this company that it's actually been found in breach of health and safety regulations. So it was just this single incident that really spoiled that really excellent record in the of safety within the company. So what do standards tell us about earthing and the need for earthing? Well, if we look at the IEC international standard, it's actually a technical specification, but that's really just a standardization term. It's a standard 60079-32-1. It's a standard for explosive atmospheres and specifically on dealing with electrostatic hazards within those atmospheres. And what it says in terms of earthing is that by far the most effective method of avoiding hazards due to static electricity is to connect all conductors to earth. And this will avoid the most common problem, which is the accumulation of charge on a conductor and the release of virtually all the stored energy as a single spark. In industry or in industrial environments where there can be potentially flammable atmospheres, there are many conductors which, if not suitably earthed, can become charged to a hazardous level. So this is as it says there, the most effective, the fundamental principle is that we need to make sure that all conductors are correctly earthed. Now that you'll find throughout all codes of practice and all standards related to electrostatic hazards. So it's one of the fundamental principles of controlling electrostatic hazards. So moving on to specifically now FIBC, for those that are not familiar, an FIBC, or a flexible intermediate bulk container, also known as bulk bags or super sacks, etc. They are typically constructed from woven polypropylene. They are roughly 1 meter cube in volume, but they can be anything from 1/4 of a meter up to 3 meter cubed. And they're used for transport and storage of dry flowable goods and powders. Now, being made from polypropylene, which is a highly insulating material, electrostatic charge can easily be generated when the bags are being filled and when the bags are being emptied. In the 1980s, there were a number of explosions involving FIBC initiated by electrostatic discharges. So that led to the development of static protective FIBC. Initially, there was no standards covering this, but in 1987, a paper by Maurer, Glor, Lutkins and Post proposed an electrostatic classification system for FIBCs. And that classification has now formed the basis of the IEC and other standards dealing with FIBC. So the main standard I want to talk about today is the IEC 6134044. It's part of the electrostatic standards developed in IEC, and it deals specifically with the electrostatic classification of FIBC. There are several sections in there. First of all, the classification. So FIBCs are divided into 4 types, type A, B, C, and D. There's also a classification for the inner liners that might be used with FIBC, and these are 3 types, type L1, L2, and L3, and there are various configurations of those different types. Within the standard, there's a section on labeling, and this is a labeling that provides essential user safety information. So it's a way of conveying to the end users all the safety requirements for the particular FIBC. There are performance requirements and also the test methods that are used to test compliance with those performance requirements, including measurements of breakdown voltage, measurements of resistance, and also ignition testing, which I'll explain a little bit in following slides. And there's also guidance for safe handling. So you can see within this standard, there's a fairly comprehensive set of requirements and guidance on how to construct, how to test, how to use safely FIBC in hazardous areas. just a quick look at the other standards. And I say I'm not going to go into detail about these because they all, in their own way, either reference the IEC 6134044 or contain very similar requirements. So the first of those I've already mentioned is the 60079-32-1. And this is an IEC standard that supports the IEC EX conformity assessment system and the ATEX directives in the European Union. NFPA 77 is a North American standard, and it's the recommended practice on static electricity, which is very similar in scope and content to 60079-32-1. And then there's two specific standards on combustible dusts in NFPA, and that's NFPA 652 and 654. And these are currently being consolidated into one document, NFPA 660. Another standard or technical report is the Japanese TR42. And again, this is very similar in scope to NFPA 77 and the IEC 60079-32-1. And then there's also a German equivalent of that, the TRBS 727. So throughout the whole world, there is a series of standards, both national and international, that provide very detailed guidance on the requirements for the construction and safe handling of FIBC in hazardous areas. So moving on to the specifics of the IEC 6134044, and first of all, the classification. As I said, there's four types, the type A, B, C, and D. And first of all, type A is a bag which has no static protection. So there's no anti-static additives, no conducting threads. It's just basically a plain polypropylene container, and these cannot be used in any hazardous zone. So they're not permitted for use in any gas zone or anywhere where you have combustible dusts. Now, type B is very similar in construction to type A in that there's no specific anti-static additives or no conducting threads, but they either have a very thin coating or no coating at all, which means the breakdown voltage is low, less than 6 kilovolts. And this is required to avoid the highly energetic propagating brush discharges that might cause ignition of combustible dusts. So because you have this protection against propagating brush discharges, you can use this type of FIBC in the dust zones 2.1 and 2.2, provided the minimum ignition energy, or the MIE, is greater than 3 millijoule. Now, in theory, but not in practice, brush discharges can ignite combustible dusts with an ignition energy less than 3 millijoule. That's in theory. It's never been shown in practice, but theoretically, a brush discharge could ignite a dust with an ignition energy less than 3 millijoule. So the requirement is that you can use these provided the minimum ignition energy is greater than 3 millijoule. If you want to use an FIBC in a gas zone as well as a dust zone, so in zones 2.1 and 2.2, then you need full static protection, and these are provided either by a type C or a conductive FIBC, or the type D. So the type C, these are typically made from fabrics containing conducting threads, and the resistance to earth from any point on the bag needs to be less than 10 to the 8 ohm. The important point is that the FIBC shall be earthed according to manufacturer's instructions. And with the FIBC earthed, they are safe for use in both the dust zones 2.1 and 2.2, and where you might have explosible gases or vapors, so in the zones 1 and zone 2, in the explosion groups 2A and 2B. So not for the most sensitive gases like hydrogen, but then you're unlikely to be using an FIBC in those zones anyway. And then there's also the type D this is a later development of a static protective type of FIBC. And this is an FIBC that does not require earthing. They provide the same level of protection as a type C, so they can still be used in the dust zones and in the gas zones, zones 1, zones 2. But there are a couple of extra requirements. The ignition energy of the gas or vapor needs to be above 0.14 millijoule, and the charging current needs to be less than 3 microamps. Provided those requirements are met within the application, then you can use a type D quite safely. The safety label, and I've shown here the safety label for type C. As I say, this is intended to provide essential information to the users. So these labels are normally displayed quite prominently on the side of an FIBC. Normally they're along the top seam of the bag, and I'll show you a picture a little later. But this contains all the information that an end user needs to be aware of. First of all, there's an indication that the FIBC has static protective properties. So anytime you see a shield on a label, that means it's providing protection against a certain hazard. And in this case, the little lightning flash indicates that it's providing protection against static electricity. The type of the FIBC is clearly displayed, in this case, a type C. And then the requirements for earthing, both of the FIBC itself. So there's a statement there that says the FIBC shall be properly earthed according to manufacturer's instructions. And also that personnel and other conductors need to be earthed. And again, there's reference there back to the IEC 60079-32-1 that gives more guidance on the requirements for earthing. And then also the important information and where the FIBC can actually be used. So it's saying there that you can use that FIBC safely. It's permitted for use in dust zones 2.1 and 2.2, and also in gas zones 1 and 2 with explosion groups 2A and 2B. So it's specifying very clearly on a label where the FIBC can be used. So the correct operation of a type C FIBC, as we've said, is that it needs to be properly earthed. And that allows any charge that builds up on the bag. And a type C typically are made these days from a grid of conducting fibers. So the whole bag itself is not conducting, but you have a grid of conductive yarns or conductive fibers. Sometimes they may be just single stripes, but those stripes will be interconnected via conductive tapes at all the seams. And that conductive grid gathers all the charge and conducts it safely to Earth. So it's using the Earth, the planet, as a big charge sink, really, to quickly dissipate all the charge away from the container. The issue comes, though, if that Earth connection is not made or becomes detached from the FIBC. Charge will still build up. Even though the bag is conductive, it doesn't stop the charge building up. And the charge, if there's no Earth connection, initially has nowhere to go. But it's looking for somewhere to go. That energy that is built up in the bag wants to be dissipated. And if the bag is approached by an Earth conductor, and that might be it might be a person, it might be a forklift truck, any Earth conductor approaching the bag will eventually create a spark. That's driven by the electric field between the bag and the conductor, and eventually that will reach the breakdown field for air and a spark will occur. And that is now the conductive path to Earth. So all the charge now that's built up on the bag and on that conductive grid will very quickly be transferred into that spark gap. And that will release a very large amount of energy. So all the energy that's stored on that bag will come off in a single spark, and that will almost certainly ignite any flammable gas or vapor present, and will ignite most combustible dust as well. So an ungrounded or an isolated type C are actually far more dangerous even than a type A with no static protection, because all that energy is being released. And it's very likely then, if you're operating in a hazardous area, that an ignition will occur. So what are the requirements for earthing type C? Well, the FIBC, according to the standard, shall be equipped with one or more designated earth bonding points, which shall be clearly labelled. So this is a picture of a type C FIBC, and you can see the big safety label, which contains all that important information for the user, clearly displayed. So this is telling the user that the FIBC needs to be earthed. And then we have these designated earth bonding points, and these need to be accessible on all sides of the container. So whichever orientation the bag is, there's always an earth bonding point visible. And the earth bonding point in this case is a piece of conductive plastic, which is sewn into the side seam of the bag, and all of those bonding points need to have a clear label. So the standard requires that this earthing symbol be used, and it indicates to the users exactly where they should be connecting earth cables. So you have both the safety label telling users that the bag should be earthed, and labels indicating where the earthing should take place. We also need the correct infrastructure. So you need to have an accessible and clearly identified functional earth. In other words, somewhere for that earth cable to be connected to. So you're connecting one end to the bag, but you also need to have a clearly identified functional earth for the other end of the earthing cable. And of course, you do need adequate earth bonding cables and clamps. You also need to make operators aware of the need for earthing, and this comes in the training, and it really should be part of the standard operating procedures for FIBC operations. Of course, no matter how much training you do and how much awareness you try to give to operators, there's always the risk of human error. So there is the opportunity, and this should be considered certainly, is to use earth loop monitoring systems and interlocks. So an earth monitoring system is basically, you have two connections to the container. One of the connections, and this is an image taken from News and Gale that produced the Earthright system. And one of the connections is the connection to Earth. There's also a connection to a monitoring system, which is monitoring the resistance to Earth through the FIBC, making sure that it's less than 10 to the 8 ohm as required by the standard. And it gives an indication that it could be a display of lights, so a red light, green light, or it may be an alarm that will sound if the resistance goes above 10 to the 8 ohm. There's also the opportunity to connect the monitoring system to an interlock, which will be linked with the process control equipment, which will stop the flow of material into the bag or out of the bag if the earth connection is not present, or if it fails during filling or emptying. So that's a very useful system, which will eliminate a lot of the possibility of human error when handling type C. Another possibility, if there's any concern that earthing may not be present, so it may be that a manufacturer is filling bags themselves, and they're able to have the infrastructure in place to earth bags, but then they're shipping bags out to all sorts of different companies, some large companies, some smaller companies that may not have the infrastructure for grounding FIBCs. So an alternative is to use a type D, and these are a safe alternative to type C in that they provide the same level of electrostatic protection, but they don't require earthing. Instead of dissipating charge via an earth cable to earth, they actually use a process of corona discharge to dissipate charge into the atmosphere. So they're using the the mass of the atmosphere as a charge sink, as opposed to the mass of the planet. The corona discharge mechanism is driven by special yarns that are woven into the fabric, and these act like, in effect, passive ionizers. So from promoting this corona discharge effect that allows charge continuously to dissipate into the atmosphere. Now, there's no simple way of determining or testing these bags like you have with a Type C, where you would measure resistance to earth. But what you have to do is make sure that no incendiary discharges can be produced from the bag, and we do that by ignition testing, and that is described in the IEC standard 6134044. So this is a photograph of the test rig that is compliant with the IEC standard. All the testing is always done on full size FIBC, and it tries to simulate the actual filling and emptying conditions. Most of the tests are done during filling. There are also testing done while the bag is being emptied. And to charge the bag, basically there is a hopper with, you can just see at the bottom, the top of a pile of polypropylene or polyethylene pellets, and these are conveyed through a conveyor and then dropped down into the bag through a charging station, and this applies charge to those pellets so that the charging current is 3 microamps. Now, 3 microamps in electrostatic terms is a very high level of charging. It's the type of charge or the level of charge that you might get when a bag where you have a large spout at the bottom and you open the spout and all the contents are emptied very quickly. That's the sort of level of charge that we're talking about. But we use that charging mechanism at the top to ensure that we get that charging artificially during the filling as well as during the emptying. And then the operator has an ignition probe which is directing a flow of gas over an earthed electrode, and that creates a localized flammable atmosphere, so that any brush or spark discharge coming from the bag will have to pass through that atmosphere to the earthed electrode. And the gas that we use is actually ethylene, but it's controlled to have a minimum ignition energy of 0.14 millijoule. And that's considered to be the lowest ignition energy of any solvent that's likely to be used in FIBC handling operations. So the operator brings the ignition probe up to the bag as it's being filled with this charging current of 3 microamp. Doesn't just do that once, he has to test at least 50 positions on each side of the bag. Also any spouts, or top spouts and bottom spouts, and any labels or other attachments to the bag. So typically we'd be looking at around 250 approaches, and we do that at both low humidity and high humidity. So that's about 500 approaches, and to pass that test you have to go through all that testing with no ignition. One ignition alone will cause the bag to fail. So this really is proving the safety of Type D FIBC. So the label for a Type D, very similar to Type C. So the same symbol to indicate static protection. Again, the type designation, also where the bag can be used. In this case, with Type D, there's no requirement for earthing. So there's a statement there that says the FIBC does not require earthing. But the other thing that's common with both the Type C and the Type D labels is this statement: all conductive objects, including personnel, shall be earthed during FIBC filling and emptying operations. And then it refers to the IEC 6007932-1 for further guidance. Now, this is, to those familiar with bags, will say this is very obviously the case with Type D, because it relies on corona, and corona is driven by the field from the charge in the bag itself. As the charge is dissipated, the field will fall to a point where corona no longer occurs. The purpose of the testing is to make sure that at that point where you still have some residual charge, that there's not enough charge to cause ignition, and that's what you do with testing. But because you have some residual charge and some residual field, any nearby conductor, a person or any metal plant, for example, if it's isolated, they can induce charge onto those. So it's important still to make sure that any conducting objects are earthed. Now, there has been an argument that with Type C, because you have zero electric field, because you have an earthed system, that you don't need to have this statement. That is actually quite misleading, because the FIBC, just earthing the FIBC, does make the FIBC safe, but it doesn't make the environment safe. And I want to explain that a little more in the remaining slides. So if we look at what can happen, and just take a human being, which the human body is essentially a conductor. If you look at NFPA 77, for example, this actually lists various situations which you might find in a workplace where an isolated person can become charged to a certain voltage. So just working at a bench, if the person is not connected to earth, they can generate 6 kilovolts. Opening a vinyl envelope for work instructions, 7 kilovolts. And you can see just these everyday activities like getting up from a work chair, 18 kilovolts, walking across a carpet, for example, 35 kilovolts. So we can generate very high voltages on a person just doing these normal everyday activities in a workplace if those people are not connected to earth. So just to illustrate the danger of this is an experiment that's carried out with an isolated person. And this is an experiment with a Type C FIBC. The FIBC itself is connected to earth, but the test subject, as you see in this photograph, is standing on a sheet of polythene to make sure that they are isolated from earth. There's an operator that's holding an ignition probe, and this is the same ignition probe that's used in testing Type D. But again, in this case, it's just used to create a localized flammable atmosphere next to the bag. And the test subject is charged artificially by connecting to a high voltage power supply. And in this experiment, the subject is only charged to 7 kilovolts, which going back to this table from NFPA 77 is at the bottom of that sort of spectrum of voltages that can be generated. So once the test subject has been charged, he then touches the FIBC next to the ignition probe. And on the next slide, you'll see the result of that experiment. Okay, so you can see there, this is the Type C FIBC. You can see the grid of conducting threads, and this is the earth bonding cable. You can see now that a charged isolated person touching that bag when there is an explosive atmosphere in the area will cause an ignition. So just because the bag is earthed doesn't make the whole system earthed. Just because the bag is earthed, it doesn't mean that the whole system is safe. We still need to pay attention to nearby conductors. So in summary, Type C FIBC must be correctly earthed before and during filling and emptying operations in hazardous zones. We can consider the use of earth loop monitoring and interlock systems to ensure FIBC are correctly earthed, or consider the use of Type D FIBC in applications where earthing infrastructure is not present or where earthing cannot be guaranteed. And irrespective of the type of FIBC used, whether we use a Type C or a Type D, personnel and all other conductors must be correctly earthed. So that ends my presentation. before I take any questions, I'd just like to follow up on Pedro's earlier announcement of the Electrostatics 2023 conference. Just to correct Pedro slightly, the actual date of the conference is 4th to the 7th of September. It's September, not November. The conference this year is organised by the Institute of Physics. The conference, as just Pedro was explaining, are essentially every 2 years we have this international conference. 2 years ago, or actually last year, was the conference organised by this working party of EFCE. This year, the conference is organised by the Institute of Physics. We have some great invited speakers, including Simon Egan from Solvay in France, who will be talking about the Solvay method for estimation of risks and fires involving electrostatic ignition. We have a Professor Machi Norris, who will be talking about electrostatic measurements, which might be very relevant in industry. And Professor Kadiri from University of Leeds will be talking about triboelectrification in powders. So there's lots of very good papers in the invited talks, and also I'm sure there'll be more in the contributed papers, which I think you'll find of interest. Abstract submission deadline, if you are interested in submitting work, is still open and will be open till the 30th of June. And if you are interested either in participating or submitting papers, you can either contact Jenny Griffiths at the Institute of Physics, or there is a website which gives all the relevant information and has abstract submission system. The website's a little long there, but if you just search for Electrostatics 2023 in a search engine in Google or Bing or whatever, just search for Electrostatics 2023 and I'm sure you'll find the conference. Okay, thank you for your attention.
So thank you, Paul, for this presentation. I will say to the next speaker, which is me, to be shorter. It's been a little long, so we have time for one, maybe two questions. There's one question in the Q&A section by Adil Ibrahim, and the question is, how do you prove charging currents are less than or equal to 3 microamps for type D?
That's a good question. That is something that the end user will need to determine for themselves. There are test methods that can be used for this. A typical way to do this is to use a metal container, and for example, you could use a 200-litre steel drum connected to if you isolate the drum from earth, but then connect it through a current meter to earth, you can measure the charge coming from the system via effectively using the container as a Faraday pail. So you would have a current meter or an ammeter connected to the drum and then to earth. So you're measuring the current that way. You have to be careful doing that you're making those measurements when there is no flammable atmosphere present. So it's something that you have to be careful of. But that's one way to do it. Another way to do it is actually to take the powder or the granules and do the assessment in a controlled laboratory environment. Again, essentially trying to simulate the flow process, but in a controlled environment where you have definitely certain that there's no flammable atmosphere present.
Okay. I cannot see more questions from the audience. I only have one, maybe last question for you. This kind of type D FIBC, does it need any maintenance? I mean, if it relies on corona discharge, I guess there are some needles or wires, small wires, producing this corona discharge. But if they are dirty or rubbed, how can you assess this is still working after some time of using the FIBC?
Again, it's a good question. In the case of type D, the corona is basically textile fibers that are woven into the fabric. They're conductive or quasi-conductive fibers. There needs to be a lot of contamination on there before they stop working. Okay. Typically, they're woven every 20 millimeters, so there's a lot of them throughout a bag. They don't all need to be working. And again, they're covering the full length of the bag, so there's plenty of opportunity there. There is, again, it's on the label that the bags of the electrostatic properties, and this applies to type C as well. Contamination can affect the usage, but typically bags they're either single trip, so they're only used once, so they don't become heavily contaminated. If they're used multiple times, they are generally refurbished between uses, so they'll be sent somewhere where dust is either pneumatically blown off the bags using compressed air, or they're actually washed. They can be put into washing machines, and the bags can actually be washed to remove any contamination.
Okay, so okay, we are not in time, but we still have a question for the audience. This is very important. So one new question, Michael Olson, probably the last one now. He thank you for your speak, Paul. And he said, just to understand, you're right about the risk of FIBC type C, the earthing bag. The outside sheet of bag can possibly be influenced and get that person charged. Can possibly by influence get a person charged. I repeat, the outside sheet of a bag can possible by influence get a person charged. Is it possible?
No. With a type C FIBC, if the bag is properly earthed, the surface of the bag will be at virtually zero potential, virtually at earth potential. So there's no possibility of the container itself inducing charge onto a person. But that person, if the person is isolated from earth, will become charged via normal activities within the workplace. So just walking around, getting up from chairs. If that person then touches the FIBC, because the FIBC is at earth potential, the person is at a higher potential, several kilovolts potentially, then a discharge can occur, which can cause ignition. So the bag itself, the fact that the bag is earthed does not mean that there is no risk. There's still a risk, and you still have to make sure that people and other conductors nearby are earthed.
Okay. Okay, so thank you, Paul. I think now it's okay. We don't have time for more questions. Thank you for a very nice and interesting presentation, an important presentation, I think, because we still have incidents with FIBC. So we will move to the next presentation, which is mine. I will share my screen. Just to say a few words about myself. I haven't said it before. I'm now currently the chairman of the working party Static Electricity in Industry, but I come more for the electrical engineering field than the chemical engineering field. I work for many years now on electrostatics. I started my PhD in France in 1997, and it was also on electrostatic properties of materials. And now I'm a teacher of the Polytechnic University in Valencia and working on high voltage and industrial electrostatics. So I will move quickly to my presentation. Here it is. Sorry, I cannot see. Okay, so my presentation is about electrostatic comfort. Let's say a not very known field. It's a summary of our experience in the last, let's say, 15 years working on electrostatic diagnostic of process and facilities. And in many cases, there were some complaints from people working on offices or even at homes. And although it's, let's say, considered a minor bother, if electrostatic discharge are repetitive, they can become a psychological problem. So we have investigated a little on this electrostatic comfort concept. We'll say some words about this, and then we will talk about standards where we have good news and show you some practical case. I will try to stick to the time. As I'm the chairman, I will control myself. I have a clock here, so I can be as fast as I can. Okay, let's talk first about comfort. Comfort is a very common, popular concept, but from a technical point of view, it's not so easy to define. Let's say the Cambridge Dictionary says that it's a pleasant feeling of being relaxed and free from pain, something wished by everybody, I guess. A perfect situation, unless you like emotions. But if you want to be relaxed and calm, that's the definition of comfort. But so it's a melt of psychological and physiological concept, and it's very difficult to measure. It depends on the individual perception. So there are, for example, from a technical point of view, there are definition for a very good definition for thermal comfort, for example. Also, we all will know we all know that anybody has let's say unanimity when you use the air conditioning, and someone complains it's too cold or too hot. But even if the perception is very different from one people to another, there are some let's say general rules to define thermal comfort. There's also a comfort concept in textile engineering for clothes related to skin temperature, heat flow, relative humidity, air permeability, and sometimes, and more recently, electrostatic charge. I mean, comfort on clothes has been very well defined. You have some textiles that are not easy to wear, others that are more comfortable, and it's related very often to humidity, air permeability, heat flow. So these are concepts well known. And in recent times, later in 1977, spoke about discomfort or even danger because of electrostatic propensity and electrostatic discharge. More recently, in the book coordinated by Song, there was some let's say mention to comfort in clothing. They say, for example, in textile, there can be catastrophic failure. For example, for parachutes, they can have big problems, but also unpleasant feeling and shocks. That's let's say the mention of electrostatic comfort, the clearest. And more recently, Silveli and others spoke about clothing comfort. Jamison, and who works a lot of an electrostatic environment, relates to health, to illness, or hygiene productivity protocols of electrostatics in buildings. So what we consider is comfort, let's say, not related to health hazards or accidents. If you have health problems, hazards, or possibility of accident, you have standards and you have very specific situations. But in homes and offices, you normally don't have these threats. Okay, for health, they are not related health problems. There was sometimes mentioned the kind of strange reaction on the skin of people, but this is not very clear. So in general, we don't consider that electrostatics is related to health unless new research can show some problems. So we go a step below, and we come back to comfort as a problem of bother for users. But even if it's a bother, it can be a real problem because it can be repetitive. It can generate a perceptible pain, not injury, but pain. May cause psychological fatigue and continuous stress level. People living in homes with many electrostatic discharge, I've seen some cases, they were afraid of touching doors. They put plastics or insulators around handles, and every day they see this, they feel this, so it's a real problem, and they are sometimes very lost and have they don't know where to claim for a solution of this electrostatic comfort. Also in shops or commercial area, that this unpleasant sensation maybe can affect customers. So from our point of view, electrostatic comfort deserves attention from a technical point of view. And today, I would say some years before, no standard covered exactly this field of electrostatic comfort, at least in the last year. But today, there's a standard project currently under development, the IC Technical Specification 61340-6-2, which is electrostatic control in healthcare, commercial and public facilities, public spaces and office areas. Not exactly devoted to homes, but many of the recommendations described in this standard can be applied for many of the recommendations for offices and commercial area can be applied for homes too. To our knowledge, apart from this new standard which is coming, building codes do not pay attention to electrostatic problems. We search for some of them and we do not find in any mention to electrostatic problem in houses, at least at the design phase. And many times until this standard comes up, technician consultants, to face electrostatic comfort problems, they have to apply standards coming from the field of electronics or ATEX environments, which define very restrictive and costly requirements, not practical for comfort situations. Because requirements are much less strict. I will show you some examples of standards and how potentials are controlled, conductivity requirements, grounding of every system, and many of these is not practical for let's say the daily life in a house. The solutions have to be cheap, of course, easily applicable, definitive, and not relying on users' expertise or training. Also, you still have some incidents like Paul described. You are supposed to have trained people working on a industry or process. You can ask them to wear anti-static shoes to be effectively grounded and so on, but not for users at homes or commercial areas or so on. So that's these requirements are not easy to fulfill for electrostatic comfort from point of view. These new standards, the project that will appear very soon, I hope maybe this year or next, gives guidance on how to control static electricity in office areas and public places. And it applies to the interior design of public places, retail and office areas, staircase, offices, meeting rooms, airports, train stations, shopping, restaurants, so on. And it includes guidelines for architects, interior designer, and facility manager, which is a novelty on the standard world, let's say. As an example, in this standard, and I will show other requirements on the standard, and maybe Paul can then complete because he's very, very active on this standard project. For example, as a general rule, the maximum of 10 to 9 ohms for the grounding path, footwear and floor of the personnel is kept. The problem is how do you ensure it, but at least this condition is kept. It comes from other standards. If we have a look to the 61340 standards in general, they refer to ESD protected areas or for electronic equipment, and then electrostatic voltage must be kept at least below 100 volts, sometimes even less. This is a very strong requirement for comfort. And from a comfort point of view, 1000 volts may not be even noticeable by a person. So you can these measures work, but are too much for comfort point of view. For the technical specification 6007932.1. Okay, this is for ATX zone. So again, electrostatic potential should be controlled below 100 volts. Grounding with a resistive path of 1 mega ohms. Discharge time of less than 0.1 seconds. That's too fast for electrostatic comfort. I think some seconds could be enough for electrostatic comfort. Some American standard, again, 100 volts, 10 to the 9 ohms for grounding path. There's also a standard which we look inside to define what is to find out how can be measure or quantify the feeling of electrostatic discharge. So in this standard, technical specification 60479-2, there are some curves and some threshold for perception and pain given for different waveforms of applied voltage. Very often for AC, but also there are some information for discharge from charged capacitors as a source of hazards. Normally, it's let's say oriented to people getting discharge from a highly charged capacitor, but it's more or less a symmetric problem. So one person is a capacitive. It's a capacity if it's isolated from ground of about 150 picofarads, and the opposite problem. These people as a capacitor discharging on a grounded object, it can be considered as the same problem. In this standard, there's a curve where you have charge and voltage. Sorry, it's in Spanish because I have the Spanish version. And then you have some thresholds in energy, and energy are these straight lines. Capacity, this straight line also. And then you can see if, as a function of the voltage, capacity, you can see what is the perception. This is the perception zone. And here it's the, let's say, pain zone. Or below this cube, you have no perception of the discharge. If we take this cube, it's not exactly adapted for comfort problems because we are around 100 picofarad or 150 picofarad charging, and this point is outside the curve. The 100 picofarad is not on the graph. We can extrapolate. And if we consider the closest point, 1 nanofarad point B or 330 picofarad point A, in the energy of these 2 points, and we try to extrapolate to let's say a human person, these 2 points, then we get as the level of perception between 1,800 volts and 3,000 volts, more or less. Some standards like EN 1814 say that it's around 3,000 volts for perception level of majority of people. This new technical specification indicates 2,000 volts, something in the middle. So of course you cannot give an exact voltage level for perception, but it's around this level. Let's say we can more or less say that 1,000 volt is not a problem from electrostatic comfort point of view, but it's a problem for many other. For ATEX zones, for electronic handling, so we don't need to limit so strongly electrostatic potential. From a point of view of energy, the technical specification 61479-2 speaks about 0.15 or 0.5 millijoules for the lower limit of perception, and 5 millijoule approximately for pain threshold. And we try to make some, perception of discharge depends on many factors. If, for example, a very simple experience that not always works, but in dry condition can work. If you approach you are charged and you approach your finger to a wall, you have a point, a discharge concentrated on one point, and it hurts because the current density is high in where the discharge appears. But if you approach your flat hand to the wall and you have many simultaneous discharge point, the feeling is less strong. You can sometimes even hear the noise of the discharge, but you don't have pain. So you can make this simple experience. Sometimes it works, not every time, but it works. It depends on the hand and the wall. But it works, and so it's not easy to predict what will be the feeling of someone approaching, so a charged person approaching a grounded object or floating object. These standards indicates that current density for pain threshold, so the concentration of the current in one point for contact area through legs, but this is difficult to translate into a value for electrostatic. It has not been investigated, so there are no specific energy for perception threshold. We try to make some calculation using, let's say, the human body model of standard, which is for electronics 610042, and let's say the current of a discharge of let's say for 4 kilovolts and 100 picofarad, the discharge current has this shape. And if we calculate the energy of this as a triangle, approximation as a triangle, the energy of this discharge and the pain threshold given before, we can see that about 39 to 55 amps, very rough numbers, are the peak current that can induce pain. We cannot make the same calculation for perception because we don't have the information, but probably it's below this. As a reference, 150 picofarad capacitor charged to 4 kilovolts is 15 amps. So if we consider that perception threshold is 1-2 kilovolts, so let's say this is below 15 amps, the current you can feel. Probably 10 amps or 5 amps, but we don't know. Okay, there's no information about this. So let's see some practical cases with maybe as the most interesting thing. One, the most common, of course, is when you are standing from a chair and you get charged. You leave the chair with one charge and you with the opposite charge. We have measured potential of people during this operation, and if in a chair you can we make this very simple experiment. We measure potential of people. It was 1,200 volts at that occasion. Not a very important potential, but relatively high, with a time constant in that case, discharge time very long, which depends on the shoes on the floor of these people. And we only put a conductive surface on the chair. There's a kind of conductive surface cell for making chairs anti-static with a grounding point, but we did not ground it because grounding of a chair in a home is really very boring. It's annoying because you have a cable and you cannot move the chair. So just making conductive the surface, then the voltage becomes much less important. It's not acceptable, let's say 200 volt, well, there's a problem of offset, but let's say 200 volts, this is not acceptable for ATEX or for electronics, but it's acceptable for comfort. You cannot feel anymore. Another question, if this conductive surface is also comfortable from a non-electrostatic point of view. But this is something that can be used very easily. In a house where they have a very expensive armchair, very big and expensive armchair that gave them a lot of electrostatic problem. I remember the kids of the house with the hairs standing up because of electrostatic charge. They wouldn't want to, they couldn't return the armchair, so they have to keep it. And finally, they use cotton sheets on the surface, and that reduced it didn't really completely solve the problem, but at least reduce a lot this electrostatic charge generation because of the triboelectric properties of the surfaces. Then we, after many measurements we made with grounding of chairs and electrostatic potential when standing up, we have a surprising conclusion. If we grounded chairs, not anti-static chairs, but normal chairs with metallic frames. So in some cases, the users ask us if it was useful to ground the metallic part of the chair. And we have this cloud of points with no obvious relation between the resistance to ground of the chair and the voltage created. So it's not so easy to find a good correlation. Grounding chairs may also produce usability problems, and from our point of view, it's preferable to use anti-static chairs, completely anti-static chairs, or anti-static covers of the chairs. So a chair not designed for electrostatic from an electrostatic point of view may work or not if it's grounded. Because the textile can be where the charge is produced can be far from the grounded structure, and no charge conduction can be done. So it's not this is not a very good solution. In this technical specification, there are recommendations for textiles, which make reference to other standards to measure how could be the textile used from an electrostatic comfort point of view. And they are related to voltage decay after corona charging, or the use dissipative materials according to textile standards, or also perform friction test and see if the electrostatic potential is less than 1000 or the charge density less than 2 microcoulombs per square meter. The problem is that can be too late. If you are not considering electrostatic problem when designing the house or choosing the furniture, then after this, solving the problem is more complicated. And we must admit that in commercial products for houses and offices, the anti-static products are not very available on the market and normally are more expensive. But it depends if some, let's say, marketing arguments can be put forward and cost is not very high. Maybe in the future we can have easily available anti-static fabrics for houses. The problem with floors, it's for me the most dramatic and the complicated. There are two problems. Electrostatic charge can be generating when walking, but also an insulating floor can avoid charge dissipation on charged people. So they have the two problems. Electrostatic, this is a typical cure where people working on with non-antistatic shoes or non-antistatic floor, and you have at each step when you raise your legs, you have these voltage peaks, you are charging, and then when you stop, it takes some time to get discharged. Here is not really a big problem. It's around 1000 volts, but we've measured more than 8000 volts easily. So the problem is that normally you cannot make any action on the shoes used by people. You cannot predict what will happen. And more and more in public and commercial area, the EVA soles in shoes is growing. So rubber and plastics in the soles are increasing the problem. The problem is normally detected once the floor has been installed. And okay, you can use conductive paintings, but are not generally not very nice, gray or dark, sometimes blue, but that's not so common. So it's not very aesthetic to use this painting. Very often this is not an acceptable solution. You can also add some, you can put some conductive laminate floor that exists and it works. We've measured it and it works. We tested in our lab conductive laminate floor and it works. But it's expensive again. at least you have it's a nice floor. But if you already spend a lot of money in a very nice floor, which is not anti-static, and then you have to spend again money on laminate floor, it can be a problem. Normally, it's considered an expensive solution for a minor problem. So it's difficult to find this solution once the floor has been installed. There are conductive additives, some products you can add when you're cleaning the floor. They have a short effect during sometimes, and they are expensive than normal cleaning products and maybe difficult to find in stores. I will speed up because I see time is over. For carpets, you can also, carpets give a lot of problem, provide a lot of problem. You have anti-static sprays for carpets, they can be used. They need maintenance, so that can be okay for hotels, but I don't know for domestic users if this can be a good solution, but it exists. The new problem is with artificial grass. It is being used more and more because it's nice. Of course, it's not anti-statics. If you use a conductive carpet below, you can reduce with measure. Artificial grass with where walking you reach 9 kilovolts can be reduced with 1.5 kilovolts with a conductive mat below. But we are not sure that it works every time. It worked in one measurement we did. There are anti-static artificial grasses, but not very easy to find either in the market. From our experience, in general, the rule of 1 gigaohm, 10 to the 9 ohms, it's like in industrial standard is okay. It has also been taken in this new standard coming, but it does not alone this for floors, this warranty electrostatic comfort. It depends also on the interaction with people. That's a very, very well-known problem with electrostatics. Probably the simple solution is to improve air humidity in order to reduce charge generation. Anti-static laminate floors, or some action can be taken before the installation of the floor. We work with in one case with marble floor, and they put a conductive mesh below, but it was difficult to predict the final result. It thinks at the end it works, but it's a risky operation if you cannot make some tests before installing the floor. We also work, I will skip this because I have no time, on problem on supermarkets with trolleys. It was quite funny. With this new floor, trolleys get charged. They put a chain on the trolley to ground it, but let's say here, with this grounding just hanging from the metallic structure, it was not very effective because the metallic surface was covered with an invisible insulating surface, and if you connect this grounding chain to a metallic part, the metallic will then it work. So sometimes you have to be careful how you ground these metallic structures. Another case was with we saw with a car parking. When you approach the ticket to the check-in machine, users get some discharge. What we did is to put a aluminum band before this check-in machine. It was very nice to see, because the car, we connected to a electrostatic potential measurement the car, and the car really raised his potential. When the front wheel touches the metallic band, it completely get discharged, because the front the wheel, okay, the pneumatics are conductive and connected to the engine, so they completely discharged. The rear wheel did not completely discharge the car, but it was enough. If you put a large enough band and close to the validating system, it was enough to neutralize the potential of the car. Humidity, there are some rules. Normally, it's the dew point which must be surveyed. But let's say for 20 degrees, simple general rule is relative humidity between 15 and 16 or more can reduce electrostatic charge generation. Finally, we skip this because it's been too long, and I will have time. I would like to have time for questions. That's the effect of people working. That's the potential that Paul showed before. If the humidity is raised, that can be reduced. But again, keeping humidity between some limits can be expensive for some system, or some climate conditioning system are not prepared to control humidity. So just say some basic rules. Consider at the design state, not rely on users, of course. Solution permanent, inexpensive, aesthetical, and little, if no maintenance. Conductivity of floor is important. Conductivity mats can be used for chairs or covers, and it is not necessary to ground it. Cotton covers can also be as a solution, a partial solution in some applications, and humidity control, if possible, it's a good solution. That does not change anything on the design of your house or office. This okay, a conclusion I will skip. Let's say as pedagogy, because sometimes when we go for electrostatic problems, the user does not understand, and you say it's a power line problem, a power substation problem with AC voltage, which can induce some problems, but do not induce electrostatic problems. And sometimes users are difficult; they do not really understand it, so you have to make some measurement with them, show them their potential, how they are getting this potential when standing up from a chair or from an armchair, and make some pedagogy and be patient, because for you it's obvious, but for the user it's a problem, can be stressed and very unhappy with his solution, and he's not technically aware of this problem. We published this work on the Journal of Electrostatics. It was presented during the Electrostatic 2022 conference and published at the Journal of Electrostatics. So here I finish my presentation. Sorry again, I did not stick to the time. Sorry. Now we can leave some room for questions. I think there's one. No? Yeah.
Shall I read the question to you?
Does air humidity change the feeling?
Okay.
Okay, sensitivity pain linked to electrostatic discharge, from Jean-Luc Revel. That's a good question. I don't have any data about this. We want to perform this test. We are making a setup for perception threshold on people. We need many volunteers, and we are working on this. But we cannot put them on a climate chamber, so we get only data with the humidity at that moment. It's referred to the conductivity of skin, and we think that can be also an influence on the sensitivity, but I cannot give you data about this. Okay, if there are no more questions, let's move to the last presentation. Probably at the end of the presentation, if someone has a question or general question, we can also try to answer them. So let's move to the last presentation from Gustavo. Gustavo, let me share my screen again for one moment. So Gustavo he's a doctorate in electrical technology, materials, and generation at the Polytechnic University in Valencia, in Spain. He worked on these materials he's going to present, the piezoelectric response of foam polymers. He is specialized in piezoelectric polymers and smart materials for MEMS application and finite analysis method for electrical applications. He's currently working at the company Aplicaciones Tecnológicas S.A. as a researcher in the high voltage area. So please, Gustavo, and sorry for being late. The floor is yours.
It's okay.
I guess you will also exceed the time, but let's try to keep in time.
Okay, I share my screen. Let's go. Okay, thank you, Pedro, for the introduction. It's an honor for me to participate in these talks. I go very fast. Okay. My presentation guide is about piezoelectric materials, focus on polymer, but we need to talk about how piezoelectric is, different piezoelectric materials, properties of that materials, more relevant, and then the presentation will focus on polymers, piezoelectric polymer forms, how to activate these polymers, the system of measurement that we use of characterizations, and application, and the conclusion. Okay. Piezoelectricity is the property of certain materials to generate an electrical charge in response to applied stress or strain. And this material will deform by an electrical field is connected. Piezoelectricity material can be natural in forms crystal, like more known crystal like quartz and tourmaline, or can be synthetic. We talk later. In fact, our piezoelectric material ability to produce charge is directly related to its crystalline structure than all of material that are synthetic want to imitate that piezoelectric ability. No? When this material will lengthen or shorten in response to an applied voltage. This is known an inverse piezoelectric effect. For example, the production of a synthetic material like a ceramic is made by a strong electric field and high temperature, and this material will be permanently polarized and convert in piezoelectric. Okay. I like to talk about history because we can understand all the things that happen at the present with this material. Okay, this phenomenon was known by 16th century with the properties of tourmaline. And this phenomenon was first observed and registered by Pierre Curie and Jacques Curie in 1890, who discovered that certain materials, preferably crystals, exhibit a small electrical charge when subject to a mechanical pressure. Then, in the early 20th century, scientists continued to study piezoelectric materials and discovered that several ceramic than the most important at that date, barium titanate, exhibit this property with a high piezoelectric coefficient. In 1960, the development of the new piezoelectric material as lead zirconate, we know nowadays as PCT, is the most used piezoelectric material because it has a great high sensitivity and operation temperature very well. Now, we focus on polymers history. Is shorter than the ceramics, but regarding piezoelectric polymers, the discovery of a strong piezoelectric effect in polymers date back to Kawai in polyvinyl fluoride, in 1969, and then it followed by discovery of pyroelectricity in this polymer by Nakamura and Wada. The science and technology of piezoelectric polymer has been dominated by PVDF family from 1982. And because the principal property is the high temperature work and low cost production. Also, the problem with polymer is the low piezoelectric coefficient constant. The work on cellular polymers date back date back to contributions of Olainen and Kirchhabainen in 1989. It was the first work and has a patent. In 1999, Hillebrand published the first model of electromechanical response of this material. And in 2000, they published the equation that ruled the model for foam polymers as sensor and actuator. Since that, and nowadays, all the paper shows new application and improvement in piezoelectric constant and temperature behavior as well. And that is all at the moment. Okay. This material, talking about the general piezoelectric material, the most important coefficient is the piezoelectric charge constant that is called D. That is the polarization generated per unit of mechanical stress applied to a piezoelectric material, or is the mechanical strain experienced per unit of electric field applied. This material we will see has a three-dimensional vector, but in our case we use 2 dimensions because the material is thinner. Okay, this coefficient D has two numbers. That the first number indicates the electric field in the direction when it is applied, and the second number, it is the direction of stress applied. For example, if we have, as we see in the picture, D33, for example, that means that the induced polarization in direction 3, the axis Z, is parallel to the direction of in which ceramic element is polarized per unit of stress applied in direction 3. Thus, this means that the pressure is in the same direction of the polarization. Or maybe we have a D31. This means that the unit stress is in the direction of the axis J or X. This coefficient has units of Coulomb per Newton. If we press the piezoelectric, or that has meter per volt if we apply an electrical field. Okay. Also there are many other coefficients to characterize this material. One important is the voltage constant G, is the electric field generated per unit of mechanical stress. We also have the permittivity constant that we will see later how to apply this in the equation of the DC3 constant. Electric, elastic and complaints. Young modulus. The young modulus is another parameter that influence a lot in the response of this material. And another important coefficient is the electromechanical coupling factor that indicates the efficiency which this piezoelectric material convert the energy into electrical to mechanical energy and vice versa. Okay, now in this table we can see the most important piezoelectric materials and the properties of it, and we can see the two most important materials like lead silicon titanate and barium titanate that has a similar D33 coefficients, but the difference with it is the temperature of working of each one. That is because the lead titanate, as now PCT, is the most used element nowadays. Also, we can see in this table the only polymer PVDF, and there is obvious the difference of piezoelectric coefficient response below than the other materials. Ceramic piezoelectric materials has many applications. The list will be extensive and we can't finish with it. But nowadays, these are the most important, like, for example, like accelerometers. Also, one of the relevant applications is in liquid flow meters. This is innovative because the material sensor is outside of the pipe of the tube, and this is a system very cheap, and there is no need a lot of work and to realize a measurement. Also, we can buy in some places this kind of piezoelectric for energy harvesting. That is a polymer with ceramic piezoelectric that bend and is used to charge small capacitors or small batteries and main focus in IoT devices. And another interesting application is the piezo cable. This is a coax cable, and the electric of the cable is made by PVDF. And when the cable is pressed, a charge or voltage is generated proportional to the stress. This cable has many advantages in certain applications because it is shielded and allowing to use in high EMI environments. Okay, focus on polymers, piezoelectric. I divided in 3 main groups. We have the first group called ball polymers. They have cavities and they show piezoelectric properties on account of its dipolar moment generated by its molecular structure. The best known is that we talked before, PVDF. From this, there are several options with elements like trifluoroethylene that it has offered a higher ferroelectric polarization to PVDF and better thermal stability. We have another one, polypropylene C, that is known for its insulation properties, but these piezoelectric properties is below than PVDF. Second one, we have the composites. This kind of piezoelectric material are tendency of the future materials because these join the best properties of each one. For example, when a piezoelectric ceramic is in the polymer matrix, then has a coefficient of piezoelectric coefficient of ceramics when mechanical property of the polymers. In this case, there are many of composites like PM and PT with PCT. Also, we have a macro composite, which is based on the rod polymer arrangement, was used in acoustic and energy harvesting application, zinc oxide, and many. focus in this work, we have the third area with voided polymers. We have polypropylene, polyethylene, those polymers we use in our works. Another interesting voided polymer is PTFE, thickness film, and of course the electrode that is similar to a voided polymer, because the electrode is a larger charger and one layer of air. That this is well known as microphones and large extended. Okay. Our work was based in a closed polymer foam that belong to polyolefin family. We can find this polymer commercially and is inexpensive. There are several densities that depend on application. We can see in the picture a closed cell and open cell. That property depends on the fabrication, and for all necessities we need that closed cell polymer, because we need to generate a macro dipole inside of the voided with air. This polymer are made by melting the plastic, and then it is produced a gas dispersion inside of the polymer, giving the voided structure. Depending on the process, the result might be in open cells or closed cells. This polyolefins application could include transportations, packaging, medical, in construction. And this polyolefin can be performed as filament, films, and pipes. Okay. These are pictures of all two materials that we use to transform Piezoelectric. This material is produced by Segovia company, and this foam belongs of the line to alveolite. That one of the principal applications of this material is in floors for noise reduction in constructions. Is the thickness form of closed cells in the market that we could find, and this form is commercialized by ton of weight. That was a problem for us when we investigated this material. On the left, we can see the polypropylene polymer foam that has a thickness of 1 millimeter and closed cells, of course. Below, we can see the cellular structure taken by an electron microscope. In the case of polypropylene samples, the ratio of air and polymer is approximately at 88%, and we use the density of 100 kilo per meter cubic. On the right, we can see another material that we use is the polyethylene polymer foam with a thickness of half on another one, 0.48 millimeters, and also with closed cells. And below, the same photo of the electron microscope. The distribution of the cell is not the same, and that was the storage of the charge inside of the bubbles was better on the polypropylene polymer. Okay. The origin of piezoelectricity in this kind of material is produced is produced on macrodipoles created by electrical discharge inside of bubble of the structure. When an electric field is applied on the thickness of the material, the electric breakdown, as we see in these linings, is produced in the bubble. Is produced in the bubbles of the material, sharing out charges on the walls inside, on the top and below. The charges are of the opposite sign on the top and below of the bubble. That is the how produce the macrodipole inside of the bubble, and then this charge is permanently for many years. To modelize these materials, we can see the voided complex structure of the polymer can be simplified by air and polymer layers, and layer on the top, on bottom for conductive electrodes. The structure comprises solid layers and air layer, S1 as called S2 respectively, and the charges on the top side on the air gap are taken to be equal in magnitude, since it is assumed that they are originated from these charges in the air gap during the pooling, because we need to produce these charges only in the gap air. The quantity of charge on electrode depends on the variation of the thickness of the material when a force is applied on it. Also, it is function of the permittivity of the polymer, but the only part that moves in this material is the air, because the polymer is uncompressible. So the DC3 charge per Newton of force will be charge density sigma that we see in this equation, divide per Young modulus, resulting in DC3 equation that is the response of the piezoelectric material in picocoulombs per Newton. In order to trigger the external discharges in void of the polymer, a high external electric field has to be applied to the samples, as we say. On the left picture, we can see the corona discharge arrangement with a tip and a ground plate, and that is the color of the corona discharge and the cone that they produce on the plate. On the right, we can see the trio de corona discharge arrangement that for a better charge surface control. In this case, the surface of the sample will be charged at the same voltage of the grid between the tip and the sample. That is the setup that we use for our measurements. In our previous measurement with corona charging with triode, we obtained the maximum piezoelectric constant in the range of 600 coulomb per Newton, and the maximum voltage range we could introduce of the sample was 12 kilowatt kV. But this is in after work, we improve the corona discharge with this new electrode. We can see in the left and on the right. This we call for this electrode corona barrier discharge. In this case, the corona is controlled, has a better control and we could obtain a higher piezoelectric constant than before. With this method, the electrode is under an insulation material that produce necessary capacitance for not produce electrical breakdown. And then the electrode put over the sample and an electric field is applied. This method simplifies the setup of traditional current discharge because the electrode only support on the top of the sample, and we need to apply a high electrical field. With this method, we could improve the DC3 coefficient, piezoelectric coefficient, to 850 picocoulomb per Newton in the same samples. Samples, in this picture, we can see the samples. The first one was made by, the electrode was made by spattering. We need to make a good conductivity electrode because we need to collect the charge of the sample when we press or when they move. And the electrode in this case was made by spattering, and we made different material of spattering like aluminum, gold, or silver. The problem with this technique that we are seeing in the picture on the right is the production of coronas inside of the chamber increase the temperature, and all samples are partially discharged. To compensate this problem, we use a shielding tape with a conductive rubber, as we can see in the figure below on the left. The only modification that we did for our material was to do a thermal biaxial stretching, because this process is beneficial to increase charge storage and reduce yaw modulus, and the result is an improvement of D33. The thermal stretching was a bit complicated, and we made this process in 4 steps, and we reduced the yaw modulus in 1 order of magnitude. But the problem with this thermal stretching is we also reduce the air and polymer percentage to 60% of range. But all this compensate, and the DC3 coefficient is more higher than before. Okay, the piezoelectric coefficient could be measured by 2 ways, by the quasi-static and dynamic measure. This is because the response of piezoelectric material changes in frequency. Each of the 2 methods can be made by direct effect, by applying a force, or indirect by applying an electric field. As for direct effect, commercial devices can be found in figure left, where sample is pressed at constant velocity and measure the charge directly on the displays. This device works at low frequency. One interesting method that we use for measure the displacement was a profilometer. The device on the right, the device can scan the surface of the sample and measure the displacement when an electric field is on it, and this device used to measure white light. Another form of measure the 33 coefficient is using acoustic methods, introducing a pressure wave, or on the other hand, introduce on the sample electric field and measure the electric pressure wave that it produces. The dynamic method by mechanical excitation is an alternative for frequencies under 20 kilohertz approximately. The setup is quite simple because it's necessary a shaker, an oscilloscope, and a chart amplifier, and we can characterize the piezoelectric coefficient. The inverse effect can be measured by a laser interferometry, the laser impact on the surface of the sample, and measure the deformation of the sample when electric field is connected. To that, we could characterize the resonant frequency from all material when this corresponding to maximum displacement. In the case of polymer foam, the displacement is in order of nanometer or few micrometers. I have to hurry. In the animation, we can see the displacement of our samples is in a range of 9 kilohertz, 97 kilohertz, and the displacement with an electric field of 50 volts was the 157 nanometers. There are several promising applications for piezoelectric foam polymers, like accelerometers that we see before in contrast with ceramic piezoelectric. The more promising application is like speakers, because it has a range in between 20 and 200 kilohertz, focus on ultrasonic transducers. Keywords, flexible, because no structuring of the sensor element in a matrix array is required, and FET transistors application. This is one of our setups, because ceramic actuators have been used in piezoelectric stacks, because multiplies effects of each of piezoelectric devices. In the photo below, we can see an actuator from a multiple ceramic piezoelectric device. We made all actuator. They are piezoelectric polymer foams with 8 samples with a DC3 constant of about 400 picocoulomb per Newton that we stack together. In the graph of the right, we can see the measurements when we apply electric field and measure the displacement with interferometer laser, how linear is the behavior of the stack with this material. Finally, concluding, piezoelectric polymer foam have an improved DC3 piezoelectric constant. Piezoelectric foam material have a better mechanical properties. Due to their manufacturing procedure, they are cheap for manufacturing piezoelectric. The corona discharge method has been improved by the electric barrier method. Exhaustive characterization was made for possible applications, and a stack of samples improved DC3 and displacement for this material. And that's all. I'm finished.
Thank you very much, Gustavo. You did the same as all the speakers. So very
Sorry.
Very nice presentation. It was very interesting, this material. I'm watching for questions. I cannot see any question. No, we're quite late, so I would just make one question. At the end, you speak about applications. What are the limits of this material for application? Because it seems a very good
Mm.
material with high dielectric constant, very easy to shape and make the integrate in any application. What's the limitation of this material? Why is it not more popular?
Okay, but it's not a good question for us, but it's a good question because this material, the only problem that has is the working temperature. After all DLC measurement, this material start to discharge between 50 degrees centigrade.
Okay.
That is our principal problem.
Is there any commercially available product for this?
Doing this presentation, I found that one company that produces samples for researching, but at the moment there isn't.
Okay, good. So it's a material for the future.
Exactly.
Okay, thank you, Gustavo. So we don't have more questions. I think it's time for closing the Spotlight talk. I would like to thank everybody for the attendance and for the participation, for the speakers, and again, EFCE and Martin. I think I hope we will continue with this Spotlight talks in the future, and of course, I hope we will meet in Berlin in September, everybody, and thank you again for your participation. Thank you.